Welcome to Super Easy Physics and Mathematics. Today we'll be looking at strategic solution to IGCSE Physics Paper 6 Alternative to Practical Specimen Paper for examination from 2023. You are expected to answer all questions and the total mark for alternative to practical paper is 40 marks. Question 1 is about the rate of evaporation. A student investigates how partly covering the top of a beaker of water affects the rate at which water evaporates. The apparatus is shown in this figure. So we have a beaker, then the mouth of the beaker is covered. The lid, there is a cover here, a lid that covered it. Then you have the thermometer to measure the temperature as it drops. Read and record the room temperature. The student pour 100 cm cube of hot water into a beaker. She placed a lid on the beaker. This leaves half of the top of the beaker uncovered. So the beaker A, she covered half of it, while beaker B, she covered 3/4 of it. So the unpainted part is the part of the beaker that is not covered, while the painted part shows the part of the beaker. So beaker B has 3/4 covered, beaker A have 1/4 covered. She records the temperature of water in the beaker and immediately start a stopwatch. She records the temperature every 30 seconds. She repeats the covering with lid B. She leaves 1/4 of the top of the beaker uncovered and then carry out the same procedure of recording the temperature. Now complete the reading on the table 1.1. No, she did so first of all, let's cover supply the column. We have the time. Time is measured in seconds. Then the temperature of beaker A, you are given the label of the column, but the unit is not given. So temperature is measured in. Then for beaker B, theta temperature is also measured in Celsius degree Celsius. Now the beaker A, the initial temperature is 8 degrees, while beaker B started with 81 degrees Celsius. Now, she measured the time, so you are expected to complete this column here. So, since she read the temperature drop every 30 seconds, so let's fill it. The first time, 30 seconds, 60, 90, 120, 150, and 180. So, the experiment, she observed the temperature drop for 180 seconds. That's about 3 minutes. Describe a precaution that should be taken to ensure that the temperature reading are accurate as possible in this experiment. Now, what you should know is that you are looking at the reading of the temperature using thermometer. So the first thing you need to do is you have to avoid having erroneous reading. So first of all, assuming the temperature is rising like this, you don't read the temperature when it is still rising. So when you want to read the temperature, you read it when the temperature, the thermometer, the liquid, the mercury have. As soon as you insert it into the cup, you only take the reading when it has stopped moving. That is when you will get the correct reading. Then the second one again is that if you want to read this temperature, you read it by positioning your eye perpendicular to the level where the bead of the thermometer has risen to. So if you look at this one, the proper reading for this temperature is 71 degrees. But if you position your eye at this level, you are going to have a reading that is higher. So when we position our eye perpendicular to the scale of the temperature is to avoid what we call error due to parallax when you are reading the thermometer. Write a conclusion to this experiment, stating for which liquid the rate of cooling is greater. Justify your answer with reference to the result. All you need to do, you look at the data that the student obtained. Now, the time for after 180 degrees second, the temperature of beaker A dropped from 80 degrees to 68 degrees Celsius. That is about 12 degree temperature drop. Why? That for the beaker B that is have 1/4 of its mouth open, the initial temperature of the beaker was 81 degrees, and then the final temperature after 180 degrees second is 73.5. That is for about 7.5 degree temperature drop. So the one with the higher temperature drop has higher cooling rate. So why the one with the lower temperature drop have the lower cooling rate? So beaker B have lower cooling rate, while beaker A has the higher cooling rate by looking at the temperature drop that she measured in 3 minutes. So let's get, what is the statement? Beaker A has a greater rate of cooling. Reason, justify, make reference to the value given to you. In 180 seconds, the temperature of beaker with lid A decreased by or dropped by 12 degrees Celsius. While the temperature of beaker with lid B decreased by 7.5 degrees Celsius within the same 180 degree after within the 180 degrees seconds. So now suggest an alteration to the apparatus that produce a greater difference between the rate of cooling for lid A and lid B. Explain why the variation produce a greater difference. So let's see the modification you bring to the experiment. So this is the setup. Now, if you look at this setup, you are dealing with rate of cooling. That is, the temperature is dropping. That is to say, temperature, the water in the beaker is, energy is flowing, heat is flowing, thermal energy is flowing out of the beaker. And this is taking place because we are looking at evaporation. When evaporation, the higher the rate of evaporation, the higher the cooling effect, because evaporation leads to cooling. Then the next thing we want to look at is what are the other things that can make heat energy to escape from this container. So we look at the mode of heat transfer. You have conduction, radiation, and convection. So if this beaker, if you want to reduce heat loss so that heat is not flowing out of the beaker, you need to cover this beaker with an insulator. If you cover with an insulator, or you place this beaker on an insulator, so heat cannot be lost from the base to the table. So what we need to do, we want to see how we can minimize the heat transfer out of the beaker. So if you were to perform this experiment, you cannot decide to say you want to also minimize heat loss so that only the evaporation, the open phase, will account for the temperature drop. So cover the beaker with insulator. It can be paper, it can be lagging material, or cover with wool, cover with a bit of cloth or whatever. So if you do this, why did you decide to cover the beaker? So you give the explanation. So the reason is to reduce heat transfer across the side and the base of the beakers. So that's why you decide to bring this one. But there are other modifications you can do. You can decide to say, okay, you decide to play each of the cards. So let's look at some other modification. Apparatus modification, then reason for that. Okay, place a beaker on a mat. Why? So that heat will not be prevent it loss through the base. Then use fan to blow the beaker, because you know that the presence of draft increase the rate of evaporation. So now, if you use a wider beaker, beakers that are bigger than the one that is already used. So if you discover that once the surface of the liquid that is exposed to the environment is wider, that factor, surface area, is one major factor that increases the rate of evaporation. So you can carry out any of these modifications. So anyone that you write, you state the reason. So if you say you place the beaker on the mat, you give this reason. If you are using fan, you give this reason, but you are expected to write just one of them. Another student thinks that the cooling rate is directly proportional to the percentage of the surface area uncovered. He draws a graph of cooling rate against the percentage of uncovered area to investigate this. Describe how his graph line show whether the rate of cooling and the percentage uncovered area are directly proportional. What they are trying to say here is you just draw the graph. So the graph line will be a straight line passing through the origin of the axis. So it's a straight line graph, and it will pass through the origin because they are directly proportional relationship. So we are looking at the cooling rate as a function of the surface area uncovered. Students in other countries are doing the same experiment. State one factor they must keep the same to obtain similar reading. The initial temperature of the hot water poured into the beaker must be kept the same. The initial volume must be kept the same. So, and if you want to compare and make your experiment reliable, they can also use the same size of material. They can use the same type of beaker. They start with the same initial temperature. So those are some of the way. So the initial room temperature must be the same. The size of the beaker and the type of the beaker used must be the same. Question 2. A student is investigating a resistant wire. She uses the circuit below. Now draw a voltmeter connected to measure the potential difference across P and Q. So now if you want to look at this, so current, if you connect this to a power source, you have the ammeter that will measure the amount of current. Then you have the resistor wire that is connected. You have a crocodile clip to make contact, and then you have the switch to close the circuit. Now what you are trying to investigate, a student investigate a resistant wire. So you want to look at how does the length of the resistant wire affect the resistance. You discover that the longer the length, the higher the resistance, and then the shorter the length, the smaller the resistance. So resistance is directly proportional to length. So what it means here is that how do you know that resistance has increased? If you use a longer length, your current will drop because you have more resistance in the circuit. Then if you use a shorter length, your current will be higher because there is less resistance in the circuit. So this section here, L, P to Q, is just telling us the value of the resistance. So let's see. So how do you connect a voltmeter between this place? So you have this, you connect it in this way. You connect it in parallel. to the wire. So you always connect voltmeter in parallel to the component of the circuit that you want to measure the PD across. So you have one mark drawing that. Now, the student connect the crocodile clip to a length of 90 cm of the resistance wire and measure the potential difference V across the terminal P and Q and the current I in the circuit. So we have this. This is measuring the PD across P and Q. So if you look at the value, now you know according to the scale of your voltmeter and ammeter, I want you to understand this. Look at the spacing. This is 1 and then this is 2. So what is the spacing between? So between 1 and 2 have been subdivided into 10 equal spaces. So each of them will now be 1.1, 1.2, 1.3, 1.4, 1.5. So you have that. So if you have this is 2.5, then the next one 2.6. So the voltmeter is 2.6 volts. Now let's go to the ammeter reading. If you look at the ammeter reading, you have this is 0.2 ampere. Then the next one is 0.4 ampere. So in between, this is 0.3. So that means between 0.2 and 0.3, it has been subdivided into 5 equal spaces. So each of these small one is going to be 0.02. So you add it to this. So this is 3, 3.2, 3.4, 3.6. So this is the ammeter reading here is 0.36 ampere. Now, the student then connect the crocodile clip to the length of, initially he used 60, then he started reducing the length. So he's varying the length. He used 40, and the second length was 60, then the third length he reduced it to 40. So you discover that as he's reducing the length, so let's see, if you reduce the length, what is going to happen to resistance? Resistance will reduce. So if resistance reduces, what will happen to current? Current will increase. So let's analyze the table and see how it look like. So first of all, let's put the value that we just measured when the student used 90 cm length of the resistance wire. What was the PD? Okay, first of all, let's complete the unit. Potential difference is measured in volts. Current is measured in ampere. So resistance is measured in ohms. Then you have the resistance per unit length. That is resistivity. So the unit is going to be resistance ohm divided by length. So this is how you get your unit. Now let's put the value. The first one was 2.6 volts, ampere 0.36 ampere. Now with this, you can calculate the resistance. Now first of all, let's look at the relationship now. I told you that the longer the length, the higher the resistance. So let's see, when he used the length of 60 cm of the wire, resistance is directly proportional to length. So the longer the length, the higher the resistance. So if the higher the resistance, that will be what? The smaller the current. So let's compare these two. So when he used 60, he decided to use a shorter length of resistance wire. So the resistance has reduced. Once resistance reduces, current will increase. So you see current increase from 0.3 to 0.49. And then also know that the higher the resistance, the higher the potential difference, the PD. So if you look at the 90, 2.6, so if you reduce the resistance, reduce the length, potential difference will also reduce, because the potential difference is directly proportional to the length of the resistance used. So we have that. So for us to measure that, calculate and record the resistance of each length of the wire. Use So once they give you the formula, all you need to do, carry out your substitution. So let's see. The first one, resistance is PD divided by the current. So PD divided by the current. So that gives us 7.22 ohm. So you can just maintain that 7.22 ohm. Then calculate the resistance per unit length, divide by this, cm divided by 90. So you do the calculation for each of them. This to get 5.10, 2.5 divided by 0. That, punch it on your calculator. Then 2.3 volt divided by 0.74 ampere will give you 3.11 ohms. Now let's calculate the resistance per unit length. So what you need to do, divide 7.22 ohm divided by 90. So that will give 0.0802 ohm per cm. So do the same thing here. 5.10 ohm divided by 60. Then 3.11 ohm divided by 40. So this is your value. So you have the resistance per unit length. Since it's the same wire, you're supposed to have the same value, but you can see that the value is just slightly different. Okay, let's see resistance per unit length. Another student suggests that the value arrow resistance per unit length for each length of the wire should be the same. State whether the result supports this suggestion. Justify your statement with reference to the value. Now, the result supports the suggestion. Why? The value is that those value, the difference in the resistance per unit length is less than 10%. So within the limit of experimental accuracy, the difference between 0.0802 ohm per cm and 0. is, so you look at this, when you subtract it, is 0.00048 ohm per cm, and this value is less than plus or minus 10% difference. So with it, so you can accept it that the material is the same material, because the difference in this difference that was registered in the resistance per unit length might be accounted for.
Subscribe and we will help you to easily upgrade your performance to an A+.
SEPAM is the solution to better grade.
Which explain why different students doing the experiment carefully with the same equipment may not obtain identical results. So that's how you say that we have to talk about experimental accuracy. So there are factors that bring error into the experiment. What is the difficulty? You have difficulty of measuring the length of the resistance wire when you are clipping, positioning your crocodile clip. So you have difficulty to judge the position of the crocodile clip when you want to clip it. Okay, and then when students want to measure the length, so when they don't clip it in position of 90, if you clip it and there's a difference of, instead of 90 and you put it on 90.1 or 90.5, so it's not accurate, so it will affect the value of the resistance. Then difficulty to measure the length of the wire to the nearest millimeter, so the contact between the crocodile clip. So once there's an error, it introduce error into your reading. Then you have the difficulty to interpolate reading on meters between graduation. So if you are taking, so you have error due to parallax. If you are reading your voltmeter, you are reading the PD on the voltmeter, and then you are reading the current using the ammeter. So what you should do to avoid this particular error, you take your reading when the pointer stops swinging, and when you want to read the pointer, you position your eye vertically above the pointer. You don't look at it from the side. So you have. Now let's look at this next question. A student finds that during the experiment, the wire become hot because there is a high current. He decides to use a variable resistor to prevent this. Draw X in the circuit to show where a variable resistor is connected for this purpose. So if you want to connect a rheostat, why do we connect variable resistor? Is to keep the current in the circuit constant. So to do that, all you need to do, you connect the variable resistor in series with, so you connect it in series. So if you want to connect it in series, you can position it here. So you are connecting it in series with the resistance wire. You can put it any of these points. It can be here, it can be here, it can be here. So any of them. So let's assume, so we put it there. You connect the rheostat, the variable resistor, in series. Now in the space below, sketch the symbol, a rectangle and an arrow. So that is the symbol of a variable resistor. Question 3. A student investigates the magnification produced by a converging lens. Very good. He is using the apparatus shown. So what are they? You have a rail bus having the rail bulb. Then in front of the rail bus, there is a triangle here that is illuminated, a hole. Then you have the lens holder. Then using a converging lens, convex lens, or converging lens. Then you have the screen here. So the distance between the illuminated object and the lens, this is the object distance. Then the distance between the lens and the screen is the image distance. So how do you get the magnification? Most time when you have a magnifier, the object is said to be magnified. The image is magnified if once the image distance is higher than the object distance, you have a magnified object. And then image distance, the distance here is shorter than the object distance, you have a diminished object. That is, the image will be smaller than the object. So let's look at the experiment. And now when we are performing this type of experiment, the image here will be formed on this screen. But when you want to read it, you use your ruler to measure from the middle to this point. And most times as you are trying to take this reading, your hand may block the light. So there are those issues. So how do you resolve the problem of you are trying to read the image that is cast on the screen? So what you need to do is you have to use a modified screen, a screen that is translucent, so you can just read it from the back. You put your eye here and you read it from the back, so you can measure from the back, so your hand will not block the light. So that is a more technological modification you can do to this set of apparatus so that you can get your reading accurately. So instead of reading from this side, so what do I call it now? This, we'll call this the left hand side. Instead of reading, if you are reading from the left hand side, your hand will block the ray of light that is going to form the image here. But when you read from the right hand side using a translucent screen that is calibrated. Now, the illuminated object consists of a triangled hole in a piece of card. Now, measure and record the height of the triangular hole. This is the illuminated triangle on the rail bus from which the light will escape. Okay, so this one will now become the source. So let's look at the size. So you measure the height. So all we need to do, position your ruler, and then, so if you look at that from here, that is 1, 1.1, 1.2, 1.3, 1.4, this 1.5. So the height of the hole is 1.4 cm. So let's now look at the image that the student, so it was focused on the screen. So now this is the image. So now to produce this image of, so let's measure. So you put this above and then below. So you see that that's about 4.5 cm. Now the student repeated the experiment using the image distance of 30 cm, 40 cm, 50 cm, and 60 cm. His result are shown on the table in table 3.1. Now measure and record the first row, the height and height of the image. So using this result and the equation, calculate the magnification. This is the reciprocal of the magnification. Magnification is supposed to be image size over object size. But in this setup, this experiment is modified. So, and that is why when you are answering alternative to practical question, follow the instruction given on the practical. Follow it step by step, because there might just be a modification different from the normal way of conducting the experiment that you are used to, that you did in the class during the period of preparing for this exam. So I've said it before that students that do well in alternative to practical are students that follow the instruction and just follow what is given to you in the examination question, and don't try to answer the question based on what the way you know that the practical ordinarily should be done. So you look at it, so they are taking the reciprocal of the magnification. Now calculate the value m and record it on the table. So we have already measured the height of the image. So we have 4.5. So we can calculate what was the size of the hole. The size of the hole remained the same, which is on the ray bus. We measured it as 1.4 cm. So if you divide that, so you see the magnification is 0.3111. So since it's a recurring decimal, you just take one of them. So these are the value that we have. To the next, we're going to graph with it. Now plot the graph of image distance on the y-axis and the reciprocal of magnification on the x-axis. You do not need to start your axis at the origin 0, 0. So let's draw. So the first thing, so we have our value, the image distance, so it will be on the vertical axis. So we have that one. So you label the axis, and then the horizontal will be m. So for drawing this and labeling the axis, you have one mark. Then for putting your scale properly, that will give you one mark. So this and this, so you have one mark. You're scaling this one mark and one mark, so you have two marks already. So let's see. We plot those values, and then finally you got this. Okay. So this is, let's look at the scoring of the graph. So for labeling your axis, you have one mark. Those are this plotting of graph in the physics IGCSE alternative to practical is always 4 mark. So these are the 4 mark. Then proper scale, so like this, you have 20, 30, 40, 50, 60, and 70. So if you get this scale very well, and then you got this scale very well, 0.5, 1.0, 1.5, 2. So if you distribute your scale on the axis properly like this, you have your 1 mark for the proper scaling. So even without plotting the graph, you already have 2 marks out of the 4 marks. Then the next mark will be for plotting the point. So the examiner is going to record the proper plotting of this point. Is going to look at any 3 out of the 5 when you are marking. So you get 1 mark. Then the next one is for you to be able to draw the line of best fit. So drawing the line of best fit will give you the next mark. That is the 4 mark that you get when you are plotting. So this is how your graph will be scored. So take note of it. So even if you can't plot the graph, another way you can get some of the mark, you can get these first 2 marks. So just indicate your scale and the axis, and then you get your 2 mark. Then you can leave this remaining 2 mark if you don't know how to plot graph for the examiner. Now determine the gradient of the graph. So let's find the gradient. So you put your triangle. So if you do that, once you have put your triangle, so you can now draw. Now if you look at the triangle, you must take the triangle where the curve, the straight line, pass through the center of the grid. So you see where I have taken, and then this triangle must cover more than half of the line. That is the standard. So don't go and take a very small angle. So don't take something small. You have to make it big. So now let's draw. So let's look this, the vertical. So if you look at this, this is 23 and then to 24. So what is the rise, the difference? So the delta U is going to be 37 cm. Now let's look at how the run. So we look at this 0.5 and then this point here 2.8. So if you look at it, so S2 take away S1, so that will be 2.2. So you know magnification has no unit, so it's a ratio. So look at that. So let's now calculate the gradient. So you have delta U over delta M. So substitute your value. So give us this. Then value for you to be marked accurately, your value must lie between 15 and 17. So we are within the range. So describe one difficulty that might be experienced when measuring the height of the image HI. Suggest an improvement to the apparatus to reduce this difficulty. So if you look at it, what do you do? Handle blocking the ray that form the image of the screen. I've explained this earlier. Then use calibrated translucent screen to replace the opaque screen. Now let's go to practical planning. That's the last one here. A student is investigating the factors affecting the size of hole a ball make when it is sand. Now plan an experiment to investigate one factor that may affect the size of the hole. The apparatus available include metal balls of different size, a tray of sand, dry sand. Now if you want to do this, you need another additional instrument. You need your meter rule to measure the height. Then if you have the mass, you need your balance to measure the mass of the ball. So now write a plan for the experiment. In your plan, you should 1. State which factor is being investigated. This is 1 mark. State a key variable to keep constant, 1 mark. That is 2 mark. Then list any additional apparatus that you need. I've just mentioned a meter rule and a balance, 3 mark. Explain briefly how to do the experiment procedure. This 3 mark. Then state how. So we have 1, 2, 3, 4. Okay, 4 mark. State how to obtain reliable result for this experiment. 5 mark. Suggest a suitable graph to be drawn for this. 6 mark. Then for one additional information that you will give as you are doing, you have to repeat your experiment. And after that, when you drop the ball on the sand, it's going to create a hole. So before you drop it the second time, you have to make sure that you flatten the top of the sand. So you have 7 marks. So planning experiment is always 7 marks. So see, let's take each of them one by one. State which factor is being investigated. So that is the first 1 mark. I investigate how the diameter of the hole is and vary as the mass of the ball drop was varied. So if you look at it, so once you use a ball of bigger mass, how does it affect the size, the diameter of the hole? So I'm talking about from end to end. So you measure that. So you have 1 mark for stating that. State a key variable to keep constant. Constant variable, that is a major where you have your points. I kept the height from which the ball is dropped above the sand trail constant. Very good. So variable. Then list any additional apparatus needed. Okay. Extra apparatus needed. That is the 3rd mark. I use meter rule to measure. I need meter rule to measure the diameter of the hole form, and then balance to measure the mass of the ball to be dropped. So you have, now we have gotten 3 marks. So to explain briefly how to do the experiment. So the procedure. Then state how to obtain reliable results. Also part of the procedure. So let's run through it. Okay. So if you look at it, I selected the ball, measure the mass using the balance, and record the mass mg. Then I drop the ball from a fixed height of 100 cm above the sand, and I measure the diameter of the hole created. Okay, I flatten the surface of the sand and repeat dropping of the ball again using the same mass. So you see, you have 1 mark, those 2 marks there. So how will you have to make sure you eliminate error. That's why you repeat it for each mass. So see that. Now, I repeated the dropping of the ball twice and calculated the average diameter of the crater that is formed. I selected 4 other masses of ball and repeat the step. So for each new mass of ball. So now we have gotten 6 marks. So let's go for the 7. Now, suggest a suitable graph to be drawn from the result. So we have the diameter of the hole that is created on the sand as a function of the mass of the ball. So you vary the mass of the ball. So in this experiment, there are 2 variables. You have the dependent variable and you have the independent variable. So when you are plotting your graph, the independent variable should be your x-axis, because as you vary this one, it produces this result. So you use the mass to produce the diameter. So the diameter, this graph, the diameter is a function of the mass. So you always make the independent variable the x-axis, and then you plot the dependent variable on the y-axis. So this is how your graph is going to look like. It's planning of the graph. So by the time you do the experiment, you will see the result. So you cannot compare. That's analysis. Answer is based on what we are given, but we are not asked to analyze this question. So now I plotted the graph of the diameter as a function of the mass of the ball drop to see how they vary. So I've done that. So that is the 7 mark. So we have gotten all the mark. So with that, we've come to the end of this practical. Subscribe to Super Easy Physics and Mathematics. Share the video, and if you like the video, please like the video so that YouTube can recommend it for other viewers.
Subscribe and we will help you to easily upgrade your performance to an A+.
SEPAM is the solution to better grade.